So we have covered quite a bit of material this semester so far. We've tackled sugars. We've talked about the metabolism of sugars. Um, and basically what we've got left before our first exam is going to be nucleic acids. So we're going to talk about the structures of nucleic acids, then we'll talk about some technologies. And we have our first exam 1 week from today. So my plan is to basically get through this week and reserve a little bit of Friday for some discussion, some question and answers about the exam next Monday. Um, I got your learning objectives, and I'll talk about this more on Friday, but basically the way that I write exams is I take the learning objectives and I think, what are some good questions from each one of these different topics or prompts? And so on Friday, I'll go through that as well as cover some new material. Friday's material will be on the exam, and we'll get through it like that. Now, with that said, the exam will be on Proctorio. So we will not have our regular Zoom meeting. Um, you will have a block of time. I believe it starts at 8:30 and then closes at 10:30. Um, so a 2 hour window in which you can take your 50-minute exam. So what that means is if you wait until, or if you start your exam at 8:45, then your exam will close at 9:35. If you start your exam at 9, it will close at 9:50. But that also means that if you start your exam at 10:20, you'll only give yourself 10 minutes to complete the exam. So I would not do that. I just like to do that to give people, if you want to start a little bit early, you're more than welcome to, but everyone has the exact same time frame unless you have an accommodation for additional time, in which case I'm glad to accommodate that and give that additional time. So we'll go ahead and jump right in. I'll explain more and talk more about the exam as the week progresses and definitely cover a lot of it on Friday. But for today, what we're covering are nucleic acids and nucleotides. And what we've got to start out with is a sugar. Now, in molecules known as ribonucleotides, there is a sugar and it is a pentose, and that specific pentose is ribose. Now, if you think back to structures of sugars, we classified sugars as being an aldose or a ketose. And then we would also say, like, oh, this is a ketopentose, or this is an aldopentose, an aldohexose. Ribose is an example of a ketose. Now, in ribonucleotides, and I'm sorry, my tablet's being kind of funky, so it's like, okay, never mind. Now it's back to normal. Clear all these. So we have ribonucleotides, and they have a pentose, and that pentose is ribose. Deoxyribonucleotides, well, the sugar is deoxyribose, so it lacks one oxygen. One oxygen. And that's lacking in comparison to ribose. Now, here are two structures. Here's a ribonucleotide, and here's a deoxyribonucleotide. Now, it's important to recognize what this whole thing is. So, before we do that, though, we've got this structure right here, which is our sugar. We've also got the phosphate group. And then add to that, we have a nitrogenous base. So, these are the three things that make up a ribonucleotide. Now, the difference between a ribonucleotide and a deoxyribonucleotide is this right here. At position 2 prime, it lacks a hydroxide group, or it lacks an oxygen. A deoxyribonucleotide also has a phosphate and a nitrogenous base. So these are the three things that make up a nucleotide. Now, a nucleotide is composed of nitrogenous base, a sugar, and at least one phosphate group. That sugar can vary. It could be a deoxyribose or deoxyribose or ribose. Now, compared to that, a nucleoside is composed of a sugar, our five-membered ring down there, and a base, our nitrogenous base. So a nucleoside does not have a phosphate group. For some reason, what's always helped me is phosphate is an indicator that you have a nucleotide. A nucleoside lacks that phosphate. So that's something that's always, resonated with me and has been helpful for me to remember. I will ask a question, I'll show you a structure and I'll say, is this a nucleoside or is this a nucleotide? Alternatively, I could say, what's the difference between a nucleoside and a nucleotide? And it's simply a phosphate group. Now, as you can imagine, if you have more than one phosphate group, well, it's still a nucleotide. Now, what is most common to see is a a mono, di, or trinucleotide. Now, these are abbreviations for ribonucleoside 5' phosphates. So that's a pretty common terminology rather than to say, uh, sorry, it's pretty common to say nucleoside triphosphate. Effectively, what this tells you is the nucleoside is the base plus the sugar. So those two components, and then the triphosphate is at least one phosphate. So this is, in this case, tri would be three phosphates. So this collectively makes a nucleotide. And sometimes you'll hear nucleotide triphosphate, nucleoside triphosphate. Um, there's subtle differences there, and one is a little bit more accurate than the other. Nucleoside triphosphate is more accurate because if you said nucleotide triphosphate, it's kind of redundant because nucleotide suggests at least one phosphate group. Okay, so what varies between these is your nitrogenous bases. Now, if we look at a ribonucleoside, you're going to have one of four different bases. Those bases are adenine, guanine, cytosine, and uracil. Terminology that or abbreviations that you'll see for that are AMP, GMP, CMP, and UMP. These are your monophosphates. Then the diphosphates are just going to be single letter, then DP. Then your triphosphates are going to be whatever single letter corresponds to that base, ATP. Now, this is where this is a very subtle thing to pick up on, but I think that it's an important thing to recognize, and that is this lowercase d in front of those. Well, that implies that you're talking about a deoxynucleoside triphosphate. So this shows that you are dealing with something that lacks that phosphate or lacks that hydroxide group at position 2 prime. So technically, if you talk about, oh, I'm adding ATP to a DNA molecule, there's a little bit of a mistake there because you actually need to use DATP to add to a DNA molecule because the capital D in DNA stands for deoxy. So you need to kind of straighten that out. Now, other abbreviations that you should be comfortable with is NMP, NDP, and NTP. That N there means any nitrogenous base. So it's a nucleotide monophosphate, or a nucleoside monophosphate, nucleoside diphosphate, nucleoside triphosphate. Now, like I said, your mono, di, and triphosphates are the most common. What you should probably kind of get comfortable with is the identifiers of each of these phosphates. Does anyone know? Add to the chat what those letters are, what those Greek characters are. And let's start with this one right here. What's that? Alpha. Perfect. Great job. What about this one right here? Perfect. Gamma. Awesome. So when we talk about like, let's just imagine that this molecule we're talking about ATP. Let's say that ATP is involved in that reaction catalyzed by hexokinase. And hexokinase, which phosphate will be transferred onto your glucose? So we're going to make ADP. Which phosphate's transferred to your glucose molecule? Gamma, the gamma phosphate. Perfect. Great job, everyone. So we're transferring that gamma phosphate. So that means the alpha and the betas remain. This also means the alpha phosphate is bound to your 5' carbon. Now, when we look at the nitrogenous bases, I'm going to draw your attention up here in the upper left-hand corner. The upper left-hand corner shows your two basic structures for the nitrogenous bases. You have a single ring structure. This class of compounds, these are known as pyrimidines. And then you have a two-ring structure. These are known as purines. Now, your purines are adenine and guanine. Your pyrimidines, well, there are three of them, three major pyrimidines. There's cytosine, thymine, and uracil. Now, what I want you to know for this, and is important for you to know, is the numbering of these atoms. So let's start with our purines. The way that I always try to think about this is I think about this as a six-membered ring, a five-membered ring. So two different structures. Now, what I'm going to do is I'm going to number them starting with this nitrogen right here. And then I'm going to go counterclockwise. 1, 2, 3, 4, 5, 6. Now, to avoid confusion, I'm just going to scribble these out. Okay, as soon as I've done that, then I'm going to jump out to this nitrogen, 7, 8, and 9. So I always think about this as start with nitrogen and go counterclockwise. Then start with nitrogen on my other ring and go clockwise. So nitrogen counter, nitrogen, well, clockwise. So then here's our numbering: 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, this is helpful because if you're familiar at all with any sort of, or if you're interested in human health and cancer therapies, um, there's lots of modified nucleotides that are used as cancer therapies. And the reason that they're used as cancer therapies is because what they can do is, let's say that you have, I can't think of a specific one, but let's say that we add a methyl group onto this nitrogen here, this nitrogen in position 7. Well, these modified nucleotides are regularly used as cancer therapies because what they can do is they can block the cell cycle. They can be cell cycle inhibitors, they can be disruptors of the cell cycle, in which case, when you disrupt the cell cycle, then that cell that has taken on this drug, well, it's effectively going to die. It's not going to replicate. And if you think about cancer as an uncontrolled or dysregulated cell cycle, then this is a perfect thing to do. So the numbering of these atoms in these rings is very important because that's how, you work with organic chemists who design drugs, and they're going to, add a methyl group so that it will be a little bit less soluble, but then it's also going to be integrated to disrupt or dysregulate the cell cycle. Now, when it comes to numbering of your pyrimidines, it's a little bit easier because you start at the 6 o'clock position, so where this nitrogen is. And then you go clockwise: 1, 2, 3, 4, 5, 6, 2, 3, 4, 6. 2, 3, 4, 5, 6. Now, when it comes to your pyrimidines, one of them, thymine, is found in DNA molecules, deoxyribonucleic acids, whereas uracil is found uniquely in RNA molecules. So whenever it comes to DNA, we've got AGCT. An RNA molecule, by contrast, is going to have AGCU. So thymine and uracil basically substitute for one another. Now, that's also a very helpful thing to know whenever you're trying to identify, well, am I looking at an RNA molecule or a DNA molecule? Well, if that RNA molecule has uracil, or sorry, if that nucleic acid has uracil, then you're looking at RNA. If it has thymine, well, then it's DNA. Okay, so I want you to know the names and I want you to know the numbering of these atoms because what I a sort of question that I like to ask is I like to give a structure and I'd like to say, where is this modification? You know, this molecule's been implicated in cancer therapies. Where is it? Or which position is it? Okay, so now onto nomenclature. This is an important distinction. I was just talking about looking at this right here and looking at the differences. Sorry, just one tad second. I was looking at this right here and showing you all this, the difference between a ribonucleotide and a deoxyribonucleotide. And I said 2 prime, the presence or absence of a hydroxide group in the 2 prime position. That is important. And the reason that's important is because that 2 prime, well, first of all, it distinguishes between DNA and RNA, but also that 2 prime is specific and unique because if I say atom number 2, well, am I talking about the base structure or am I talking about the sugar? Well, in order to avoid that confusion, anytime you say something prime, like 1 prime, 2 prime, 3 prime, 4 prime, you're talking about the atom within the sugar ring. Non-prime numbers, by comparison, are in reference to the bases, which is another reason that we like to, when we refer to phosphates, refer to them as alpha, beta, and gamma. So non-prime numbers start at your base, or you say those in reference to your base. Then primed numbers are reference to your sugar, and then alpha, beta, gamma is in reference to the different phosphates. Now, the phosphate group may be attached to the sugar at either of 2 positions. So it's typically going to be attached to the 5 prime position, but it might also be attached at the 3 prime position. If it's at the 3 prime position, it's referred to as a 3 prime nucleotide. If it's at the 5 prime position, it's referred to a 5 prime nucleotide. And sometimes you'll hear terminology like phosphorylated, at 3 prime, or at 5 prime, or at both the 3 prime and 5 prime position. So here what we have, go ahead, add to the chat. Are these 3 prime or 5 prime phosphorylated nucleotides and deoxynucleotides? Perfect, 5 prime. Great. So we've got all of these that are phosphorylated at the 5 prime position. Now, here are your most precise name. This is an adenylate molecule. So what that means is you have the nitrogenous base, adenine. Your sugar is ribose. And then you have at least one phosphate group. So that I always like to, deconstruct the name. That ATE suffix, that indicates that you're dealing with an ion, like phosphate, nitrate, carbonate. You're dealing with an ion, so it's got a charge. Where's that charge coming from? It's coming from over here. ADE, That's in reference to the nitrogenous base. The only way that that nitrogenous base is going to be bound to your ion is through a ribose sugar. So adenylate is the most accurate name for this nucleotide right here. Now, the more common name that you'll see, and the name that I will say more than anything else, is adenosine 5' monophosphate. So that adenosine, that is going to reference, um, that's basically the ribose, or sorry, the nucleoside name, which is highlighted here at the bottom, the nucleoside name plus the phosphate and where it is. So another way that I can put this, can you reiterate the prime versus non-prime? Sure. So just a second, I will. I'm going to um, so this molecule right here is the name that I would use is adenosine 5' monophosphate. That name, adenosine, is the nucleoside, and then it also indicates where on my sugar my phosphate group is found. So if we look at this, so it's kind of highlighted in like a pinkish magenta there. That is adenosine, what's highlighted here. This is adenosine. This is the nitrogenous base adenine plus the sugar ribose. Now, in addition to this, we've got a phosphate group here. Okay. So that phosphate group, what number is it on? Well, this says it's 5 prime. That prime is very significant. And it's significant because what we want to do is we look at our sugar. This is 1, 2, 3, 4, 5. Okay. Well, if I'm asking for atom number 1, I also have numbers on my bases. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, what we have to do is distinguish the numbering of these atoms from one another. We don't go on and say, oh, this is 10, 10, 11, or anything like that. But instead, what we do is we use a prime numbering scheme. So we just say, oh, it's kind of like an organic where you had an R group and an R prime. Well, this is also a part of a molecule, but it's a little different. So we throw a prime on there. So this is 1 prime, 2 prime, 3 prime, 4 prime, 5 prime. Those primes are in direct reference to the numbering of the atoms in the sugar. Okay. So now I'm going to ask you guys this question. I'm going to circle an atom. I'm going to say it's a carbon, but in the chat, go ahead and add which number it is and make sure that you're accurate with your number. That one right there. What number is that? You got 3 prime. You're absolutely right. Okay. Now I'm going to give you another one. And this one, you might have to toggle back and forth on the previous slide or something. What's that one? Got 5. So you're absolutely right. Okay. So I bring this up because what I want to show y'all is this right here. That bond, that's a nitrogen to a carbon. Now, one of the questions that I always like to ask is this structure right here, this is a purine. This structure right here is also a purine. So which atom numbers connect a purine to a ribose? Got to vote for 9 and 1 prime. Perfect. Fantastic. Okay. So then if we go over here, what about a pyrimidine? I vote for 3 and 1. I got to vote for 1 and 1 prime. Let's jog back for a second. Here's our pyrimidine. This is a 1. You guys were all right on the 1 prime, but it is 1 and 1 prime that bind a pyrimidine and a sugar. Great job, everyone. Okay. So that's one question that I really enjoy asking. Maybe enjoy is too generous of a term, but I regularly ask. Um, so it's important to keep those numbers different and understand those numbers because that's like a convention of describing these molecules. Okay, now the last thing that I want to reference and bring to your attention on this slide is at the bottom here. These are deoxynucleotides. So we have to remember that lowercase d in front of whatever we're talking about. It's deoxyadenosine, deoxyadenosine monophosphate. That is a part of a DNA molecule, whereas adenosine monophosphate is part of an RNA molecule. So that's an important distinguishment between these two molecules. Now, like I said, these do have naming conventions. For instance, adenylate or adenylic acid, guanylic acid, cytidyllic acid, uridylic acid, deoxythymidyllic acid. The more common convention that you're going to see is the nucleoside plus primed number. So I'm just going to say number prime, and then mono, di, or tri phosphate, because that gives you a lot of information. You can say, well, it's at a 3 prime, or sorry, 3 prime mono phosphate, 3 prime diphosphate, 2 prime triphosphate. Those are the important things that you will become accustomed to seeing. Um, 5 prime is in reference to, or the primed number is in reference to the atoms of the sugar, whereas the non-primed are referencing the atoms of the nitrogenous base. Now, there's a couple of different monophosphates that you'll see from time to time. For instance, adenosine monophosphate, adenosine 2 prime monophosphate, and adenosine 3 prime monophosphate. These are your most common. But then another structure that you can see from time to time is this guy right here. Adenosine, okay, that's our nitrogenous base. 2 prime, 3 prime, cyclic monophosphate. Oh, this is an example of a cyclic adenosine monophosphate, or CAMP. That's a secondary messenger, very common in hormone signaling. So cyclic adenosine monophosphate, that's it could be a cyclization between 2 prime and 3 prime. You might also see it's somewhat common to also see adenosine 3 prime, 5 prime, cyclic monophosphate. Now, if I remember correctly, most commonly when we refer to cyclic AMP, it's this form that's the more common one, more biologically relevant one. I do believe that the 2 prime, 3 prime monophosphate does play some role, and it is a signal for some receptor proteins, but it's typically the 3 prime, 5 prime. So what that means is basically you've got, and this is kind of tough to visualize, but it's like a phosphate group that's kind of in the background here. It's like tucked behind the molecule, tucked behind that sugar ring. Okay, now with that in mind, these nitrogenous bases right here, here, and here are really pretty common in lots of different things. For instance, coenzyme A. Now, has anyone taken a functional biology class? Um, if you have you ever seen coenzyme A or coash? I'll give you a second to respond and just say thumbs up if you've heard of this or you've seen this before. And you can go thumbs down if you haven't. Okay, we got a thumbs up. Okay, so this is one of the reagents in, among other places, but it's in the citric acid cycle. Now, in addition to that, one of the things that I really like about how we've changed this curriculum, adding glycolysis, is this molecule right here, nicotinamide amine dinucleotide, NAD plus. This is in your oxidized form. NADH is the reduced form. They're effectively the exact same. The only difference is a hydride and therefore the overall charge. But NAD plus, that is a nucleotide-based molecule. Then the other one, flavin adenine dinucleotide, FAD. So NAD plus and FAD and coenzyme A, these are all major cofactors in the citric acid cycle. Now, I mentioned this previously when we talked about NAD plus and NADH. They're major cofactors, but what type of cofactor are they? They're cofactors in redox reactions. So they participate in oxidation reduction reactions. And these release a huge amount of energy. So in addition to, I think everyone's pretty familiar with nucleic acids being involved in, storage of genetic material and, the cell cycle and replication and everything like that. Um, these uh, nucleotides and nucleosides are huge components of integral metabolic processes. Just the from glycolysis, we used NAD plus to make NADH, and we're gonna use that later on. So this is like if there's like an important takeaway from this slide right here is really intended more for, hey, don't forget about this role. They're cofactors. Um, then if we're to go back a little bit, one of the important things is distinguishing and understanding the difference between the numbering of the atoms in the nitrogenous bases as well as numbering the atoms within the sugars of those nucleosides. Sorry. Then I want you to know the numbers. So that if I give you the structure and I circle an atom, you know which one it is. Then similarly, if I give you a structure here and I circle an atom, you know what it is. If I phosphorylate it at some point and I show you that structure, I want you to know what that is. The most common naming convention, like I said previously, is nucleoside plus the name of the nucleoside, which would be here, adenosine, guanosine, uridine, cytidine, plus that phosphate. Okay, so now I got a private message. How do you know something is primed? Just assume whenever it is a sugar. So the prime numbering is in reference to a nucleoside, and the numbers on the sugar, on the atoms of a sugar, are primed, are referred to as, numbered prime, whereas the numbers of the nitrogenous base do not have that prime. So if we look at this molecule right here, what I have circled. Actually, I'm gonna clear all the ink from this, and now I'm gonna start. I'm referencing just this molecule. Give myself enough space here. Okay, so numbering the rings for my purine, because this is a deoxyadenosine. I know that because I lack a hydroxide group, but I'm going to start right here on my nitrogen. I go counterclockwise. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so those are the numbers for those atoms. Now, when I go to number my or the atoms of my sugar, 1 prime, 2 prime, 3 prime, 4 prime, and 5 prime. Now, there's nothing special that has happened to any of these atoms. It's just the numbering and the naming convention. These are kind of the rules that we follow. So the what about the oxygen? Well, that is not referenced as a primed number or an atom. Sorry, that's not primed. That's not 6' or anything, because we're talking about carbons and nitrogens when we number these. Okay, so does that answer your question? Um, all right, well, that's really what I wanted to go over today. So I'm going to go ahead and stop my recording. Um, like I said previously, we've got new content that we're